In this lesson, we continue to discuss Bayes' theorem with focus on multiple hypotheses and sequential evidence. We will start with defining multiple hypotheses and sequential evidence updates. Then we will move to analyzing a couple of cases and discuss the candy problem. So far, we applied Bayes' theorem using one hypothesis and one evidence, and we computed the posterior probability of actually having cancer given a positive test, and the posterior probability of raining given a cloudy morning. Next, we are going to extend Bayes' theorem to work with multiple hypotheses and sequential evidence. Let's explain multiple hypotheses using a concrete example. Consider the handwritten digit recognition problem. So, given an image of a digit, which represents the evidence, we need to determine which number it represents. So, in this case, there's going to be 10 hypotheses covering each digit. Now, using Bayes' theorem, we are going to compute the posterior probability for each one of those hypotheses based on the available evidence. Here's another concrete example to demonstrate sequential evidence. Suppose we have Bayes' theorem with one hypothesis and one evidence, where the hypothesis states having COVID and the evidence is having fever. Now we introduce a second piece of evidence or a second symptom, runny nose, and update Bayes' theorem accordingly. As you can see, the posterior probability is written as P of h given x1, x2, and the likelihood now is probability of x2 given h and x1. Here's a question for you. Why computing this highlighted expression is a hard task? The reason boils down to the knowledge of joint probability to model x1 and x2 under h. So, given this hypothesis h, it's very hard to figure out the joint probability distribution for both two pieces of evidence. This is going to be knowledge or data that we don't have. To overcome the issue of computing the joint probability, we can make an assumption that simplifies the problem. So let's assume that x1 and x2 are conditionally independent, but under this given hypothesis. So this is big assumption we're doing here. And it makes a lot of sense. So if we think about it concretely, having a fever and having a runny nose, both symptoms arise from COVID. So they are totally independent under this given hypothesis. And if those two pieces of evidence are conditionally independent under the hypothesis, actually I can write probability of x2 given h and x1 as a probability of x2 given h. This is going to simplify the derivation and the application. Now, I will briefly show you the derivation steps for going from Bayes' theorem with one piece of evidence to a sequential pieces of evidence. Again, here's our conditionally independent assumption under the hypothesis. I'm going to use the chain rule to expand this probability expression. And then I'm going to use the conditionally independent assumption to simplify the highlighted term, do some reordering, and this term is going to simplify to P of h x1, which we already know, and this is how you go from one piece of evidence to two. And using the same logic and the same steps, we can go further to multiple steps. In this example, we discuss both multiple hypotheses and sequential ideas. And the story goes as follows. Suppose a company produces 5 types of candy bags. Each bag contains different proportions of cherry and lime candies. But the catch is these bags are unmarked, so we can't tell which type it is. But we have this very general information. So 10% of the produced bags are cherry-only bags. So let's say this company produced 100 bags, so 10 of these 100 is going to be type H1. And 20% will be type H2, 75% cherry, 25 lime, and so on. So here you have 40% with 50% cherry, 50% lime, 20% with the 25, 75, and so on. Now, what happens next is very exciting. Suppose we picked a bag at random, and we start to draw candies from this bag. The first candy was lime, the second lime, the third lime, the fourth lime, the fifth lime, and so on. So we drew 10 candies, and all of these candies were lime. We're going to use Bayes' theorem to answer the following question. What kind of bag is it? So this touches on multiple hypotheses because we have 5 bags and 5 hypotheses. And then what flavor will be the next candy, which is the 11th draw? So given that x1, x2, x3, x4, and so on, like all of them equals to lime, based on what we have seen so far, what is going to be our posterior probability about what the type of the next candy? To simplify things and without loss of generality, we wrote a Python script and computed these probabilities and plotted the answer. So as you can see, we have 10 draws in the x-axis, and we have the computed posterior probability for each draw. At the beginning, we have the prior probability, which is the 10%, 20%, and 40%. One key observation, after the first draw, we go and compute the posterior probability. You are going to get different things based on the proportions of the cherry and lime, but bag number 1 zeroed because it's out of the game. There are no limes inside this bag. As we continue to draw more and more candies from these bags, you notice that the probabilities are being updated based on what we have seen so far, also based on the proportions of lime versus cherry. So as you can see, bag number 5 or H5, things kept going better and better because this is the bag which only has lime in it, and the probability is going to get closer and closer to 1. The other bags enjoyed a little bit of a run, but eventually the probability started to decline because they ran out of limey proportions inside them, right? Here's another interesting question. So what would happen to hypothesis 5 if the 11th draw happened to be a cherry? In this case, the probability is going to drop to 0 because this bag doesn't have a cherry. And finally, to predict whether the flavor of the 11th draw candy is lime, we compute the posterior probability that the candy is lime given x1, x2, x3, all the way to x10 already lime. All of this suggests that this model has increasing confidence that the candies are coming from H5, which is the bag with all lime. So most likely the flavor for the 11th one is going to be lime. In summary, we covered Bayes' theorem with multiple hypotheses and sequential evidence.